So good morning and good afternoon, everyone. Thank you for joining us and welcome to our webinar, Bringing Data Center Flexibility into Resource Adequacy, Planning, a Case Study of NV Energy. My name is Priya Sridharan, and I'm a Senior Program Director at GridLab. For those of you who are not familiar with GridLab, we are a public interest organization that provides technical assistance and expert capacity to address technical challenges as we navigate transformation of the power system. We work across the bulk and distribution system with a heavy focus on reliability and resource adequacy, and are deeply devoted towards advancing the art and the science of how we model the power system. So coming to the topic today, since I have been here at GridLab, which has been more than 5 years, our work has included a heavy focus on load flexibility. But data centers are different. For data center flexibility to be viable, it has to consider the business context and the value proposition for data centers, which are different from other customers. For it to lower the requirement for new resource builds and help contain customer cost increases, it needs to be factored into resource planning early on rather than being an afterthought. In this collaboration with Telos Energy, we hope to demonstrate an approach for making data center flexibility viable. We want to acknowledge that several organizations are thinking about data centers and how to integrate them into the power system, including ESIG and EPRI, the national labs, and others. In fact, just yesterday, ESIG hosted a webinar in which E3 presented a data center analysis that has similarities to the work here. Our hope with this project is that it will be a useful contribution towards the excellent initiatives led by these and other organizations. With that background, I'm thrilled to introduce our speakers today, Derek Stenslick and Chris Cox of Telos Energy Group. Chris, please feel free to begin sharing your screen while I complete the Telos introductions. Derek Stenslick is the founding partner of Telos Energy, an analytics and engineering firm specializing in renewable integration, grid planning, and power system reliability and flexibility. Derek is a recognized expert on wind, solar, and battery integration, resource adequacy, and power markets. As a longtime collaborator and friend of GridLab, his work focuses on resource adequacy analysis and integrated grid planning and how it can balance risk and customer costs through the energy transition. He holds a master's degree in applied economics from Cornell. Chris Cox specializes in investment analysis and power systems modeling at Telos Energy. He has over a decade of experience in applying financial analysis, production costs, resource adequacy, and capacity expansion modeling towards power system planning and asset valuation. In addition to his experience in power systems, Chris also worked in investment banking, where he specialized in mergers and acquisitions within the telecom and digital infrastructure sectors. He holds an MBA from Cornell University and a master's degree in economic forecasting from the University at Albany. Following Derek and Chris's presentation, which will take about 40 minutes, we will conclude with a question and answer session. Please post your questions in the Zoom Q&A. Derek and Chris, the floor is yours.
All right, thank you so much, Priya, and thank you all for joining. We're really excited to share this. We think it's some pretty thought-provoking work and really appreciate GridLab giving us the opportunity to play this out and to really think differently around data center flexibility and resource adequacy. So Chris, go to the next slide, please. So I don't think I have to set the context of why we're talking about this, right? Demand of data centers is growing extremely quickly. There's also a ton of uncertainty around how much is going to show up and how much of that load could be speculative. It's also very uncertain how fast it's going to show up. And at the end of the day, well, I think over the last year or so, we've been hearing a lot about transmission interconnection challenges to bring data centers online. The next pinch point, or the current pinch point, is really resource adequacy. Do we have enough supply on the grid? And we've seen this kind of across the markets, even in utilities or in capacity markets that we always thought were a little bit long or had a surplus. That surplus is rapidly shrinking, and resource adequacy, having enough supply to serve the new data centers, is now kind of the big pinch point. I think the last bullet here, kind of really important, where we do see data centers showing up in the planning process, whether it's an integrated resource plan or in a capacity market, kind of setting up the requirements for the capacity market, we've almost unilaterally seen the data center assumption in that modeling as inflexible. It's put in either as a fixed load block, same full megawatts every hour of the year, and in some cases with an 8760, we know the data centers won't be operating at their max capacity every hour. So sometimes you'll see 8760s modeled, but certainly we have not yet seen any utility or ISO actually incorporate flexibility. The big reason for that, they're not crazy, it's that what they're hearing from the market, what they're hearing from data centers is they do not want to be flexible. But you're starting to see that that narrative start to shift, both out of necessity, because again, we don't have enough surplus on the system, and just from pure reliability. It's something that we're going to have to see one way or the other. The other kind of big motivation of this is we really want to bring some of this decision making around data center flexibility up front in the planning process. And Chris, if you go to the next slide, kind of the big key thing here on bringing that data center flexibility up front in the planning process is that's when there's optionality, right? There's optionality in terms of the utility or the ISO can trade flexibility for accelerated interconnection. While there might not be a monetary incentive to say, hey, for this data center, are you willing to curtail your load 10, 20, 30 hours a year? There certainly is an incentive to bring on these data centers faster. And so speed to market is critical. We need to get this decision making or this thinking around flexibility upfront in the planning process, because that's where the incentives are in terms of acceleration. It's also, in terms of dollars, when we're talking about trading CapEx and building new resources, we're talking about billions of dollars of CapEx at play, as opposed to if you start trying to look for flexibility after the data center is already built, well, then you're talking about dollars per megawatt hour. Even a couple $1,000 a megawatt hour in a scarcity event isn't going to be enough to move the needle. And then lastly, the other reason to really think about this up front in the planning process is that's when we have options. We have options on the grid side. We can design the system around that flexibility in terms of the new entrants or retirements that we're planning for. It's also when we have optionality for the data center design. So we can think about alternatives to backup generation that maybe can run more, is expected to run intermittently, as opposed to a diesel backup that might have air permit issues. Or we can start integrating behind the battery storage at the data center, start thinking about longer durations rather than just having a UPS to keep reliable power when switching to the backup. Maybe we add duration to that battery to actually have it be a grid resource. And so the key thing here is what we're trying to do in this study is think about how we can get that flexibility brought up front in the planning process and really in the resource adequacy analysis that is fundamentally underpinning integrated resource plans. It's determining how much capacity we need to bring on in the IRP, or it's setting the capacity requirement in a wholesale market. At the end of the day, the underpinning of both of those mechanisms is the resource adequacy analysis. So this slide, what happens, or sorry, stick on that one more second, Chris. What happens if we don't get that? We're leading to higher total capacity needs. We've seen huge challenges on the supply chain. We're out 5-6 years for new gas turbines now. We don't have incentives to use on-site generation, or sometimes we don't have air permits that allow for that if we don't plan for it up front and get it into the IRP process. And at the end of the day, utility contracts have already been set. If we don't get it into that IRP process, into the procurement process, the utility contracts have oftentimes already been negotiated at that point. Next slide, Chris. So how are we thinking about capturing large load flexibility and data center flexibility? The key thing here is we're looking at this from an accreditation perspective. While data centers are a load, we're going to treat the flexibility as if it were a supply side resource. So what I like to say is, we have challenges at time coming up with load flexibility programs or things like that. To the extent that we can get data center flexibility to look and feel and transact like it's a supply side resource, just like a generator, I think it fits directly into this procurement process a little bit better. today's framework, again, every place we've seen this in IRPs, even places with rapid data center demand growth, the data centers are treated as a firm load requirement. So if we have a 100 megawatt data center coming in, not only is the utility planning for that 100 megawatts, they're planning for the 100 megawatts plus a planning reserve margin, so call it 115, 120 megawatts. And again, that's treated as firm. Now, the proposed framework here is to actually accredit the flexibility from the data center as a supply side resource. So now, while that data center might bring a load obligation of kind of 100, 115 megawatts, we're going to say the flexibility can actually be treated like a generator and bring its own supply side to the equation. So it can bring accredited capacity to meet that PRN. The reason that's important is if we assign it on the supply side, the incentives are directly aligned with the data center. They're being treated like a generator, and there's incentives that go with that, capacity payments or lower load obligations, rather than it being socialized across the load if we just went with a lower planning reserve margin. So the key thing here is we're going to be using this to calculate capacity savings as we go through the IRP process. So if we bring accredited capacity, that every megawatt of accredited capacity that we can get from data center flexibility is a megawatt less accredited capacity that we need from the resource side. So the way we looked at this, Chris is going to go in a lot more detail on this, but essentially we looked at a menu of options. The key thing here is we don't know the exact flexibility characteristics of any data center. It's going to differ by the type, even by the type of data center, let alone other large loads. And so we try to come up with an agnostic way to look at flexibility and importantly, give a choice to the data centers of what level of flexibility or availability do they need for their business case. So we basically set it up where we have an ELCC matrix, very similar to how you think of battery storage at 2, 4, 6 hours, and you can accredit the capacity based on that. We're looking at that here as a percent availability. You can see we looked at 99.5% availability all the way up to 99% availability. So still very high percent uptime for these centers, but they can bring really meaningful amounts of resource adequacy benefit and capacity to the system. So Chris, if you go to the next slide. So the objectives, really this is about creating a framework that we would really like to see incorporated directly into integrated resource plans. So while we did a case study of NV Energy, it was really meant to inform, to really show how different utilities could embed this directly in their resource adequacy analysis, but also in their integrated resource plan. So we wanted to look at system benefits, not just do the resource adequacy to show the ELCC of data center flexibility, but show how that flexibility translates into capacity savings, avoided costs, and avoided emissions. And with that, I'll hand it over to my colleague, Chris.
Awesome. Thanks, Derek. So we're going to start off just talking a little bit about the methodology and how we thought about things here. So just to set the stage, the main tool that we used for this analysis was Plexos. So we used Plexos LT for our capacity expansion modeling, and then we used Plexos ST for our probabilistic RA and our production cost simulation work. And then for the data, primarily we were drawing from Nevada Energy's 2024 IRP. So things like the generator characteristics, our assumptions around planned installations and retirements, our load forecast, that all came from Nevada. And then we supplemented that with some data from NREL for things like capital cost from the annual technology baseline, as well as fuel prices and some information around implied market heat rates for market purchases from the EIA. So with those tools in place, we built an analytical framework to think about this. First thing we did was we prepared our load data. So we were fortunate in this case that Nevada had released not only their hourly load assumptions, but the actual data center load itself. We were able to extract that from the work papers. We made some of our own adjustments to that load forecast, which we'll talk about kind of later on in the presentation. But basically created our own adjusted hourly load forecast for the region. So thinking like 2025 all the way out through 2050. From there, what we did is we ran a capacity expansion model. So we have a kind of a baseline capacity expansion, a build out of resources from 2025 to 2050, assuming no data center flexibility. So this is going to give us our baseline capacity, our cost, our emissions, things like that. And then in parallel, what we did is we did an ELC study ELCC study with the matrix that Derek talked about, where on the one end, we were sensitizing the percent availability or uptime required by the data center. So 99.5% all the way up to 99.9%. And then we assume 2 levels of data center participation. So in one sense, we assume 1 gigawatt participated, and then in the second case, we assume 2 gigawatts participated. So we essentially had 6 scenarios that we ran this ELCC study on. And then with the results of that, step 4, we generate our data center ELCCs. We're able to model those as firm capacity resources and add those firm capacity resources back into the capacity expansion model. So we then reran the capacity expansion model for each of those scenarios. We generate a different set of capacity that gets built out by the optimization. We have different costs, different emissions. And from that, we're able to compare that back to the baseline and figure out what our avoided capacity needs are, what is our avoided cost in terms of the net present value of our capital cost or operating costs, as well as any avoided emissions. So digging into the ELCC side of things a little bit more and the capacity accreditation that we used, what we wanted to do here was to compute a demand side ELCC, stands for effective load carrying capability. So the first thing we did is we modeled our system from a probabilistic perspective to bring our system to a criteria of 0.1 LOLE, loss of load expectation, which is 1 day in 10 years. So we have our system kind of at criteria. Then what we did is we went through those different scenarios of ways to model the flexibility of our data centers or our large loads. You add that to the system, and with that flexibility, your LOLE is going to drop. We then added firm blocks of load to the system, and we keep adding more and more firm load into the system until we get back up to our original reliability criteria of 1 day in 10 years. And that additional amount of load that we're able to add from the point where we add the flexible data centers to the point where we're back at the reliability criteria is essentially what we're considering the demand side ELCC, or the amount of load that the demand side participation of those large loads is actually able to contribute to the system. So to do all of this, what we did was a sequential Monte Carlo probabilistic analysis. We used 25 weather years of data, where each of those weather years receives 20 outage draws. So we're looking at 500 samples, and we run the full 8760 chronological analysis for each one of those 500 samples. So you end up with millions of observations. And what this allows us to maintain is the chronology as well as the correlation of all of our different weather years. You get hundreds of dispatches. It allows the storage to kind of arbitrage the energy margins, both like temporally and spatially. And then in addition to all of this, you kind of maintain the correlation of your load years, your wind and solar years, as well as the hydro energy years. So that's kind of the high level framework and how we thought about things. And then I'll talk a little bit more about now the actual capacity contributions that we found and dig into the results a little bit. But just to set the stage, so just wanted to touch on a little bit of an overview of Nevada Energy's system. So today the system has a peak of around 9 gigawatts. Most of the load is in the south near Las Vegas in Nevada Power. It's about 75%. It's also where most of the generation is. Sierra Electric is in the north, and that's where about 25% of the load is. The thing is, where most of the data center growth is actually expected to take place is in that smaller Sierra Electric region. And so there's going to kind of be a shifting that's going to have to take place in this system where you're either going to need more transmission or more generation being concentrated to the north as that data center growth increases. On the left-hand side here, we just see the near-term demand growth for 2025 versus 2030. I think what's interesting here, and this is based on some of the assumptions that we made, but today data centers are around 5% of the peak load, 8% of the total energy served in the region. And in just the next 5 years, that's expected to be about 18% of the overall peak load and contributing almost 30% to the energy. So really significant demand growth from these data centers. And so it makes it an interesting case study for a system that's really going to start to have to accommodate a lot of these data centers and start to really focus on how to plan for these data centers coming into the system. What can we do to kind of make this a little bit of an easier transition, make it have less of an impact on ratepayers, things like that. And then just thinking about the load forecast a little bit. So we started with the data center load forecast from Nevada's 2024 IRP. They actually had data centers growing to around 840 megawatts by 2030, and then up to 2,800 by 2050. We increased that for the purpose of this analysis to 2 gigawatts by 2030, 4 gigawatts by 2039. Some of that is because, even after the IRP was released, there was a lot of news that came out that the growth was expected to accelerate even beyond what they were initially planning for just, 6 to 9 months ago at this point. And so, Doug Cannon, he was the former CEO of Nevada Energy, said it's absolutely foreseeable in the next several years, you could double, triple, or even quadruple the size of the electric grid in Northern Nevada. Northern Nevada being that smaller Sierra Electric region. And then developers saying that they're expecting to invest, $100 billion in the next 10 years just in the data center infrastructure. So, we thought it was appropriate to increase these levels a bit. And I think it also, for the purpose of a case study and to try to really push this methodology that we've tested, just kind of strains the system a little bit more and makes it like an interesting case study. So as I was talking about in the analytical framework, after we developed our load forecast, we ran our baseline capacity expansion model. So this is a look at what that baseline expansion looks like. You can see in the chart on the right here, this is the cumulative capacity that gets selected by the capacity expansion model that we ran. Significant new amounts of batteries and solar being added in particular, and then that gets filled in by some gas resources, which are primarily selected for their firm capacity, as well as some open positions, which are considered like firm market purchases. And all the way out in like 2050, we also see some pump storage and some geothermal getting added. One point to note is in the actual forecast, there's a lot of gas retirements that get modeled, particularly in like the last 5 years. And so we see a lot of capacity being added in that period, just trying to replace some of that lost capacity. So that's how we developed our baseline forecast. And then what we wanted to do was actually implement the flexibility in that ELCC study that we're looking at. And so the way that we actually modeled this in Plexos is we assumed that the data centers were energy limited, but in our case, it was energy limited from an annual energy limitation that they were able to provide, as well as power limited. So in any given hour, they're going to be limited based on the actual amount of demand that they're placing on the system. So the way that we thought about this is going back to that case matrix that we had, the 99.5% uptime to 99.9%, and then the max responses available. We created a total amount of energy that they could provide throughout the year. And just think about the math there. You take the 99.9% case, 1 gigawatt of response. If you're up 99.9% of the year, that means you're able to provide for 0.1% of the year. 0.1% times 8760 hours is 8.76 hours times your 1 gigawatt of response. So gets you to 8.76 gigawatt hours per year. And so we did that for all the 6 cases in the scenario matrix to figure out the total amount of energy that these resources could provide. And then the other side of it that we looked at was that in any given hour, we wanted to inform the amount of response based on the load factor of the data center. So you can see the load factor here typically varies between, let's say, 60 and almost up to 100%. And so in any given hour, like we picked hour 3800 here as an example, the load factor was 85%. If you're in the 1 gigawatt case, that means that the max amount of response that the data center could provide is 850 megawatts. So what we did is we modeled these resources for each of the 6 scenarios. We performed the ELCC analysis that I was discussing earlier, and we come up with the actual ELCC results for these different configurations. So focusing here on the chart on the right, what we're looking at here is the total supported load, or ELCC, for these different data center configurations. Just focusing on the 1 gigawatt case here. If we were in the 99.5% uptime, that scenario was able to support 865 megawatts of load of its own 1 gigawatt of load that it added to the system. And if we're more constrained and the amount of uptime is more like 99.9%, you get 665 megawatts that was still able to be supported despite that 1 gigawatt of load being added to the system. So we can take that as a percent. It's 67 to 87% ELCC is what we found for these different data center configurations. And then we also looked at what this was if you assumed an even larger amount of participation. What we wanted to do is be able to study basically the marginal ELCCs of these resources and the saturation effects. And so we did the same type of analysis, assuming greater levels of participation, and you can then calculate basically the marginal ELCC of that on the bottom third of this table. You can see that there are declining marginal ELCCs. So for the 99.5% case, we have a 87% ELCC for that first gigawatt. The second gigawatt brings 67% ELCC. So there are declines there. And in a more constrained case where you're modeling something like a 99.9% uptime, that 67% that we initially had drops just to 25% for that second block. So there certainly are marginal declines in the ability for these data centers to support the load. But I think in this system, it was really interesting. We're still seeing pretty significant amounts of load that can be supported through this flexibility. And obviously this will change based on any given specific systems configurations, but for this system, we're still supporting pretty large amounts of load. And as we'll see in later slides, they really don't have to provide energy for that many hours. So the other side of this is after we had our ELCCs calculated, we kind of round trip this and put it back into the capacity expansion analysis. And so we took our 6 scenarios, we reran the capacity expansion model where we treated the data center as essentially like a supply side resource that's able to provide the same amount of firm capacity as the ELCC that we calculated for it. And what we found is that this then results in fewer, more firm focused resources being added. So things like gas resources, and then also a delay in some of the more energy focused resources like the solar plus storage. And so on a present value basis, we saw lower overall costs as a result of modeling these resources as flexible. So what was interesting here is there's kind of a trade-off that takes place in terms of your costs and benefits by modeling these resources as flexible. So on the one hand, you do reduce your CapEx and your fixed O&M. You're able to build less resources because these resources, the flexibility itself is providing capacity essentially. So you're able to forego some of the capacity needs. But with that, by building less resources, you may end up having slightly higher operating costs because now you may not necessarily have to build as much wind or solar, or you may forego building a new gas plant. And so you may end up running like an older gas plant a little bit more. But on net, between the two, you're still able to realize a cost savings essentially. And then we just wanted to show what that looked like in terms of the actual change in additions across the years. So these are snapshots for our kind of one of the bookend cases, but this was the 2 gigawatt 99.5% case. Kind of how the capacity changes across the years. So in the earlier years, you can see that with the data centers being modeled as flexible resources, you're kind of able to get away with building a little bit less of everything. And then what we saw is by 2045, 2050 period, that's where there was pretty significant amounts of retirements that take place in terms of the existing gas fleet. And what we saw there is that we actually ended up with less new gas being built, and then more batteries and more storage getting added. And so what's happening there is, the data centers come in, they relieve some of the need for firm capacity for gas. But the need for the system then to still have that energy there is still there. And so you do end up building more of those resources because the overall energy need is still there. That kind of becomes your next most binding constraint on the system. So, I think the cost savings are great, the reliability benefits are great, but the other side of this that we wanted to then look at was, what does this actually do for the data center operators? How is this going to impact their operations? So we wanted to characterize some of those needs. And I think what we found is that overall, like in any given sample that we looked at or any given weather year, the flexibility needs are pretty manageable. And those are even more manageable if you assume that things can be spread out across an entire fleet of data centers that are participating. So what this chart on the left shows is the average hours per year that the data centers got called upon across all of the different weather years that we sampled. So each of these weather years, we did basically 25 full year simulations with different outage draws. We take the average of that. You can see some weather years require more hours of participation on average, others fewer, but in general, we're talking like less than 20, even in the worst weather year as far as the average. So the way that we thought about this was initially we have the whole data center fleet, and we took the average based on, when does this data center, when does any single data center in this fleet have to respond or get called upon for a demand response event. But in reality, it's not going to be one data center that's participating. Like in a 1 gigawatt case, it would probably be lots of smaller individual data centers. And so let's say you have an event that requires 200 megawatts of response. If you have a whole gigawatt of portfolio, all 100 megawatts each, you may only need to actually call on two of those 10 data centers to actually serve that particular need. And so we adjust our averages to account for the fact that, like in that example, it's really only 2 of the 10 that are responding. So it's 0.2 hours of response in that particular event if you average it across all the data centers that are both participating and not participating. So the chart on the right shows the average hours of flexibility per year across a couple of the different cases that we wanted to highlight. And again, we showed this data center fleet-wide as well as for any individual data center using that 100 megawatt assumption. And so for our kind of most constrained case, which is 1 gigawatt, 99.9%, we're only looking at around 3 hours for the entire portfolio on average responding. But for any given data center, that was 1.4 hours of response. In more of a middle case here, we have 1 gigawatt, 99.5% availability. So we would expect it to respond more often, and it does. Where 6.6% for the full fleet, but only about 3 hours of response for any individual data center. And then in kind of the most extreme case, we had 2 gigawatts of data centers participating, 99.5% availability required. And for that, we do start to see a larger increase in the number of hours that they're required to participate. So in this, we had almost 42 hours of calls on average. But again, if you're able to spread that over the whole portfolio, it's more like 13 to 14 hours per year. So something that probably can be managed, and it isn't too significant. The other thing that we wanted to characterize here was just the time of use of when the data centers were being called on to provide flexibility. So you can see kind of across all the different models, it's typically taking place concentrated to the summer evenings. So I think this is a benefit from a planning perspective for the actual data center operators that you can kind of plan for the times of year where this is something you need to be aware of and concerned with. In our case, in this particular system, it's not really like a winter risk. It's really more of just in your summer months and just in the evening where it's something that you need to be thinking about and planning for. And then the one other way that we wanted to characterize this was, when the data center fleet gets called upon, how long are they actually being required to curtail load or provide demand flexibility in some way. And what we found is that there really wasn't a case where there was a need for any single response for greater than 15 hours. And the vast majority of times when they were called upon, it was for 5 hours or less. And that was across all of our different scenarios that we modeled. So just, kind of putting this all together and what we think this all means. I guess, key findings here, we really do think that the data center flexibility does have the ability to offset capacity requirements and to reduce costs in the system. But there are some caveats there. I think the system does need to have a tighter reserve margin the actual planning reserve margin in the system needs to be something that's binding and that's driving capacity expansion. And then you do need a higher, fixed capacity cost relative to your variable costs. We think about the trade-offs that we are seeing in our own expansion plan. That's going to kind of drive how much additional incremental savings you can get out of this. But we found that even small levels of participation have pretty big benefits. So that first gigawatt in particular, we were seeing 60 to 85% of that load that was added is able to actually offset its own capacity need just by being flexible. The burden on data centers is pretty manageable just based on the operational characteristics that we saw, of only a couple hours a year of actually being called upon, kind of understanding what time of the day it's going to happen, and having relatively short duration of events. And I think another kind of interesting thing we found here was that the actual growth of data centers, in some ways, like the data center supply drives demand for flexibility. So as you add those data centers, it's actually going to be, pushing you towards your reserve margin targets, producing a greater risk of scarcity events. And so that actually increases the need and the value for data centers to be flexible. And then, yeah, as far as some of the key lessons learned from the study, I think, one of the big things is that there are saturation effects here. So we saw that both on the ELCC side of things, as well as on the cost side of things when we reran that NPV analysis. And so kind of taking this methodology and applying it to each specific system and understanding how those marginal effects change as the saturation levels increase, as your assumptions around uptime or participation changes, is going to be really important to really creating like effective policies and effective implementation of data center flexibility in any given region. And then, I think overall what we want to do is try to help make this data center flexibility more plannable. And to do that, it really needs to be considered more upfront in the planning process. So, data centers right now have an extremely high willingness to pay for electricity once they're actually up and running and on the ground. And so there's not typically a lot that can be done to incentivize them after they've already come online. But being able to incentivize data centers early, whether that's through accelerated interconnection by being flexible, by looking at the avoided capital costs of flexibility and figuring out a way to structure rates that share some of that with the data centers and share some of that with the ratepayers, can both be things that you can do ahead of time to really incentivize things for the data centers. And so, I think that the thing here is really trying to push that to be upfront, to incentivize the flexibility, and come up with the right incentives and changes to interconnection agreements that can then really push for this flexibility from the data centers. And then just on the last point, I think we think that this methodology can really be applied to a lot of different planning practices, to other regions, whether that's the IRP processes, capacity markets, thinking about rate design, and some of the ELCC and reliability and stochastic analysis we did could even be done by data center designers or data center operators to start thinking about ways to actually configure their data centers to fit into this capacity and flexibility framework a little bit better. So with that, I think we want to open it up to any questions. Derek, I don't know if you have any additional thoughts, but.
No, I thought you covered it really well. Thank you so much, Chris. And so Chris just flashed up the link to the report. I saw a question come in about whether these slides would be available. So this slide deck, but really a more complete version of this, we went over kind of probably half of the slides in the report. So that's up there along with a fact sheet. So you can go grab that right now. Priya, we are also going to be putting the recording of this up on that site as well, correct?
Yep, that's right. Yeah, awesome. Thanks so much, Chris and Derek. That was really, really excellent. And we have a good amount of time. I'm actually going to take moderator's prerogative and kick us off with one that's a little bit more analytically focused. Just yesterday, as I mentioned, I watched the ESIG E3 webinar, which was an interesting analysis for Virginia. It included a data center flexibility analysis. They calculated different flavors of ELCC, including first in versus last in, and not surprisingly, their first in ELCC values were in some cases an order of magnitude higher than the last in. So how does this concept of ordering come into our analysis, and how should planners, resource planners, tackle this on a practical level, as it seems that ELCC values will be dynamic given year-to-year changes? And maybe Chris, if you want to tackle that, that would be great.
Yeah, and we saw that, and it was interesting. I think they actually, for the first in analysis, found pretty similar levels of ELCCs that we did in like the 60 to 80% range. So I think our analysis is more like the first in type of approach. And that's probably how planners should be thinking about this, is how do we plan around the data center growth more proactively, and actually incentivize them early on to be able to provide this flexibility to the system. I think it is a good point that the ELCCs will change as the grid evolves or as more data centers come online and things like that. I think for our study, we took a single snapshot in terms of our reliability analysis, and we focused on 2030 to come up with those ELCCs. But I think, if, in a broader planning process, you could actually take multiple snapshots through time of ELCCs as the data center's system grows, or as your system evolves with different resource characteristics, to try to more fully capture some of those changes over time.
Awesome. There are a lot of great questions that are coming in. I'm going to actually switch to one that's a little bit less on the analytical side, but more on sort of the practical side. I'm going to combine two questions. One, which is anybody doing this already? Has it been done in any utility IRP where we treat a large load as a supply side resource in IRP planning? And then combined with that, let's say you're a data center who really wants to do this and is willing to offer flexibility in exchange for getting energized more quickly. Where can you go?
Yeah, so good two-part question there. I don't know of a utility that has implemented this in their IRP process. I'm not even sure I've seen a utility-sponsored PRM and ELCC study consider this. So I have not seen it. We have seen places where demand response is starting to get accredited with ELCC, just like any other resource. So I know Excel Colorado, in their just transition solicitation, their IRP that was released this past year, they accredited all resource types using ELCC, including demand response. So that was mostly residential commercial demand response, but at least kind of the framework is there, treating flexible demand as a supply side resource directly into the ELCC and PRM framework. So that second part of the question, though, of like, hey, we want to do this, can we do this as a way to get online faster? I think that's exactly the framework we tried to set up and try to think about with this study. Frankly, what we hear a lot in the industry is, oh, data centers don't want to be flexible, or I can't get any flexibility. They just want to run. They're not price sensitive. And that is true if the data center is already online. And so if you go to a data center today that's already operating and say, hey, can you enroll in this program, or can we pay you some money to curtail? The answer will be no. Like, they are not price sensitive on the electricity price. And so that's really the framework that we're proposing in the study, is how do we bring this up front in the planning process? Because if you go to a prospective data center and say, hey, our queue, it's going to take 5 years for us to bring on new resources, to build the transmission to get to you, and you can wait 5 years, or we can interconnect you in 2 years if you're willing to curtail 10 to 12 hours a year. The answer there will be much, much different than if you're asking them after they've been designed. And so to the extent that we can ask that upfront in the planning process, I think there's a ton of latent flexibility. We're just asking for it at the wrong time. And if you ask for it when they're already built and they're already designed and they're already on the system, the answer is going to be no. If we trade speed to interconnect for flexibility, I think the answer will absolutely be yes.
Great. I love that there's a question about load forecasting, because it's so foundational to all of the analysis and planning we do. So the question is, do you agree with the methodology that NV Energy used to discount their major project, which is their data center load, for the forecast, which was about 85% for projects with unsigned agreements and approximately 45% for projects with signed agreements? And what are the discount percentages used to inform the baseline forecast in this case study?
I can take that one first, Chris, if you want to chime in. So this is certainly the process. I don't want to diminish what NV Energy is doing. This is the process that we've basically seen in any utility IRP that we've looked at. Is they typically go down and they have some threshold at, you know, at 3 different milestones. They assign a probability at each. I think that's problematic, and the reason for that is, frankly, we don't have probabilities for the success of data centers in the pipeline. Even if you're using the success rate of data center development from 3 years ago, it's completely apples and oranges to today, where there's so much more speculative data center development going on, and frankly, data centers are shopping the interconnection queues because they know the answer might be, hey, we can't interconnect you for a few years, and so they're putting in multiple requests. So I think using historical success rate as a framework, I get a little cautious of, and frankly, if there isn't a large amount of money put upfront in the process, like very significant amount of upfront money and long-term contract commitments, I would heavily discount that in the forecast. So in some of the IRPs that we've been involved in, where we've seen the actual queue over time, there's been just a ton of attrition. And certainly, like, oftentimes the utilities are reporting the top line number because for every data center that drops out of the queue, another one is coming in. But we're just seeing a lot of attrition and essentially a revolving door on some of this. So I get very cautious around using those milestones unless it's, again, a firm contract, a lot of money upfront, and a lot of long-term commitment.
Yeah, that's great. There are so many great questions. It's hard to pick, but I'm going to try to sort of flip between the ones that are a little more regulatory and philosophically oriented versus the ones that are a bit more analytical. How different is your demand side ELCC approach from current practice, presumably current ELCC calculation practice? What would it take from a technical or regulatory IRP perspective to implement it in planning?
I think it's pretty similar to a typical supply side and kind of best practice ELCC approach. You know, I think to actually implement that, you have to take a view on what the actual operations of the demand side response is going to look like. So, you know, we came up with one framework where we're basing it on percent availability and participation to actually be able to model that and come up with the load carrying capabilities of demand side flexibility. So I think having a view on that and thinking about how this is going to work in an individual utilities market or in an RTO ISO context would allow you to kind of take a pretty standardized approach to valuing supply side resources and applying it to the demand side once you kind of come up with those characteristics of what this demand side participation can actually look like.
Thanks. Just I'll add one thing. We've seen ELCC. It started out as a way to accredit variable renewables, wind and solar, and then we saw it start getting applied to battery storage as well. And increasingly, we've seen it being applied to thermal resources. I think that the stance I take on this is, if we're going to use ELCC or some similar accreditation, we should have a consistent accreditation framework for all resources. And that can be all supply side resources. It can apply to demand response. It can apply to transmission as well. And to the extent that we can get all resources on that common playing field, I mean, fundamentally, that's what accreditation is looking to do, is allow you to compare across resource classes and including both generation, transmission, and load.
Great. Thank you. Next question. Is it safe to presume the additional energy produced to support the data center load came mostly from thermal generators? And if so, was that greater utilization, especially of existing thermal resources, enough to warrant consideration of higher outage rates?
For this analysis, there was significant data center growth, but I think we saw in terms of what the capacity expansion model is building, and in terms of what we're assuming is actually serving that load, it was mostly batteries, solar, and battery, solar, and some wind, with a bit of additional gas added on as like a firm capacity resource, in addition to the firm capacity coming from those renewables. So I think we were seeing most of the incremental loads being served by renewables. There may have, be certain instances where you have to rely on gas a little bit more, but in general, I think the vast majority of the energy that was coming was from renewables.
Yep, great. how do you interpret the marginal ELCC values? Does the marginal ELCC of 40% mean that adding a 100 megawatt data center requires the system to add 60 megawatts of firm capacity to retain the same 1 in 10 level as the no flexibility case? Or is it compared to the no data center case?
So the marginal ELCC in this case, if it was, you said 40%?
Yes.
Yeah, so that means it's able to carry 40% of the load that's being added to the system. So yeah, the other 60% would have to come from other sources essentially.
Yeah, and I'm reading the question. So we looked at the data center flexibility case relative to the case with the data center but no flexibility. So we weren't comparing back to the case without the data center at all, if that makes sense. So that was like the follow-up in that question. So thank you.
Great. Did you assume 100% uptake or compliance with demand flexibility calls?
I'd say, well, no, because for a few reasons. One is we assumed a 4 gigawatt data center fleet by 2040, and the max we looked at as kind of participating in the flexibility is 2 gigawatts, and then even earlier on in like the 2 gigawatts by 2030, we only assumed kind of a gigawatt. So we covered for that in a sense of we didn't assume all of the data centers in the entire fleet were flexible, and part of that was because we showed that decreasing marginal ELCC, like each tranche of data center, the flexibility from it is going to be less valuable because it would have to respond for even longer. The other piece to this is even and Chris talked about this on a couple slides, when the data centers were called on to be flexible, it wasn't all of the time that it required the full gigawatt or the full 2 gigawatts, right? There was times where only 200 megawatts were required to respond. And it was actually more often than not, you didn't need the entire data center fleet to respond. You could get the RA benefit from a portion of that. So even if it wasn't 100% success rate, there was still more available demand to shift than we needed.
Great.
Yeah, I think it's an interesting. I was just going to say, I think it is an interesting question though, because yeah, one thing that you could look at in further study is like you have an event where the data center gets called on and for some reason it doesn't respond, and what does that actually do to the marginal ELCCs? But yeah, in our approach, I talked about how we have these annual energy limits, and basically, as long as you still have gas in the tank and that data center gets called upon and it has enough available generation, it would, in our analysis, it would provide it.
Right. I'm going to combine two questions. One is, would implementing this require a non-firm interruptible tariff or some other type of tariff or contract defining interruptibility or some other program with financial incentives? And if it is the last, what financial incentives would be enough to get a response? And along with that, do we have a set of recommendations for public utility commissions as utilities propose data center tariffs?
3-part question. I think I got all of them. So I'll hit the one on the financial incentive first. So again, I think because we're talking about bringing this planning construct or this construct up front in the planning process, there are incentives that are enough to move the needle. And the first big incentive is speed to market. So if we can use this as a mechanism to bring that data center to market faster than waiting for supply to show up on the grid, that's a massive incentive, and that will spur willingness to be flexible. The second is if we're up in that planning process, we're talking about billions of dollars of CapEx, where the decision of, am I willing to be flexible if I can offset capital, like big billions of dollars of capital, and have that reflected in my long-term commitment? I think the answer is yes. If you're waiting, again, on the back end, if the data center is already built and you're saying, hey, can I pay you $3,000 this hour to curtail? I think the answer there will be no. But again, that's why we're trying to bring this up. I think the second part was around, do we need an interruptible tariff? I think certainly this type of analysis, our view is this type of analysis would inform the tariff. So what we're trying to show here is if you have this level of flexibility, what's it worth on the system? Like what are the avoided costs in terms of capital and generation? So this is really being used, I think, to inform those tariffs and like what's the value it brings, and more fundamentally, what's the appropriate cost allocation? Like what are the the incremental costs that the data centers are bringing, that so we can make sure we allocate it responsibly. And then if they're bringing that flexibility, how do we allocate those costs? So I think it can integrate and it should be used to inform those tariffs. But I also think there's an opportunity here because these are large data centers, they're transacting directly with the utility. There's a lot of bilateral, like just negotiations that go on with a load of this size. And so this is where you don't necessarily need a tariff to do this. It could be just done through negotiation on the appropriate tariff. And then remind me on the last piece. Oh, what can the commissions do? Yeah.
Recommendations.
I think recommendations for the commission, I mean, one is just to get this type of flexibility analysis embedded in the IRP process. So in the PRM, the LCC study, and then ultimately, like, I think first and foremost, like, let's look at what the value, the resource adequacy benefit is of the flexibility, make sure that the utilities are putting that in their PRM and the LCC studies. Second is, I mean, in the IRP in general, we should, I've been pretty strong about advocating for a scenario that shows with and without data centers to show, okay, what's the incremental cost and resource build required for the data centers, so we can cost allocate that. And then you can take that one step further and show, like, commissions could require a scenario to say, what would that look like with flexibility? Again, like, we don't know exactly how the data centers are going to respond, but if we're not doing that analysis in the IRP process and through the regulatory proceeding, like, nobody will see the value, and so that we won't even be asking the right questions. So that's what I think the commission can do, and then obviously downstream tariffs and contract negotiations, PPA negotiations, this can be used to inform it.
Great. This is an interesting question. Does it matter what the mechanism is for flexibility? It could be on-site generation or storage, workload shifting, curtailment, et cetera. I know the person who asked the question notes that I know some data center companies are interested in funding running off-site aggregated DERs or virtual power plants. Would the same analysis apply?
I think it matters only to the extent that whatever mechanism you use is there when you need it. So if running on-site generation is more reliable than a data center actually being willing to curtail its load, for example, or it's like its I2 load, then I think in that sense it would matter. But assuming that you have kind of that firm commitment, or you've planned so that when you actually need it, it's available. I think from the bulk power grid perspective, it's probably a little bit less impactful, would be my view. But I don't know, Derek, do you agree? But
yeah, I think we try to set this up in a technology, like an agnostic way. We don't care how you bring the flexibility, and that's really the reason we set it up in the way that we did in the analytical framework, is specifically to not be prescriptive. Like, we didn't model behind we had the idea of, hey, should we model like emission, like run hour permits for diesel generators, because like they're going to be hour limited throughout the year. We thought about that, but at the end of the day, we wanted to put this in like an agnostic framework that would really let data centers develop really unique applications. We're already seeing companies out there that are developing data centers from the ground up to have the flexibility. And so what we want to do is say, here's the value. And again, like, create that matrix that gives a menu of options. You can give that to the data center developers and they go, okay, like, I can get 99.9% availability really easily, but to go to 98% availability, that's going to be really hard. So like, we can use that information to help design it from the ground up, and that's why we took that agnostic route.
Great. We're at time. I think we can maybe slip in maybe two more what I think are fairly quick questions. And for those who do need to hop off, we'll try to follow up with you on the questions that you've asked that we weren't able to get to. I think this should be a short one. Do these outage hours consider that data centers are not uniformly distributed throughout NV Energy service territory?
So for the purpose of this study, we modeled NV Energy as essentially like a single bubble model. So we weren't necessarily focused on like transmission constraints between Nevada Power and Sierra, or like within any given region. So for this analysis, I would say it did not.
And then
I think it's certainly something that they would be planning for in like in a real world situation.
Right, great. Did our study consider any alternating current impacts? For example, power quality impacts, bar support, other AC considerations?
Yeah, so this is not a transmission kind of impact study. When we're talking about the flexibility and potentially curtailing data centers, we would not be taking the view of like instantly disconnecting a gigawatt of load instantaneously on the system. Obviously, that would have power quality challenges both for the data center and for the grid. And so when we think about in the resource adequacy timescales, we're really saying, okay, we're planning out hours or days in advance around this flexibility. And so both the system and the data centers could make sure they do that in a responsible way, both for the grid impact and the behind the meter load.
Great. I will note that we had a separate GridLab study done in partnership with Elevate, which did dig into exactly this question, and we'll put a link to that report in the chat. I think that would be useful reference for the person who was asking this question. Okay, well, I think we managed to get through quite a bit of these questions. This concludes the formal presentation or the formal portion of this webinar. As we mentioned earlier, the report, the fact sheet are on our website. We pasted that in the chat already. And once we are able to upload this video to that website, we'll also send out a final note to all of the participants. So with that, I want to thank everybody, including our speakers and all of you for joining us for this webinar. And we hope that this work is of interest. And please feel free to reach out to any of the three of us if you have any additional follow-up questions or want to continue the conversation. So thank you so much, and yeah, have a great rest of your day.